In this part of 1.3, our objective is to develop and use a strategy for finding limits. We want to be able to evaluate limits by dividing out and rationalizing techniques. This is usually the order to follow when finding a limit analytically. First, we always try direct substitution. That's just a plug and chug method, meaning plug in a number, work it out, and if it works, great, we're done. If direct substitution doesn't work, we want to try to factor. That's usually the next best option. Rationalize is when we multiply by the conjugate. You'll see some examples of that. Simplify, or get a common denominator. That's what we're going to think of when we want to simplify. Expanding is multiplying out. The special trig limits, you're going to have to memorize what these look like. The limit as x approaches 0 of sine of x over x equals 1, always, and the limit as x approaches 0 of 1 minus cosine x over x equals 0. Highlight these, box them, star them, do something, memorize them. Whatever it takes, you need to learn to recognize these and evaluate them when you see them. Now, the first one could be seen like this. Because of the reciprocal property of 1, we flip this over, we still get 1. Similarly, the second one could be seen like this, the cosine of x minus 1 instead of 1 minus cosine x. That still equals 0 because subtracting it the opposite way is still going to give us 0. So memorize them, be able to recognize them in any of these forms. Squeeze theorem, we'll talk about a little bit later, and a graph or a table is the first thing we looked at. It just usually takes longer to do that method. When you evaluate a limit, usually starting by direct substitution, and you find that you're getting an indeterminate form, what that means is you evaluate and you get 0 divided by 0, or infinity divided by infinity. These forms tell you nothing. From these forms, you cannot determine the limit. Therefore, you must find a different strategy to manipulate and find the limit. First one. Remember what we always try first. Always try direct substitution first. I'm going to try it. X approaches 2, so I say, let me try to plug in 2. Notice how I'm not writing limit because now there's no x, there's a 2 over 2, and that is square root of 7 on top, 2 on the bottom. That's determinate. I have a value, so that limit can be determined. Done. I don't have to do anything else. See how easy that is when you try direct substitution? Second problem, I'm going to try direct substitution here. 1 squared plus 5 times 1 minus 6 over 1 minus 1. I get 0 on top, I get 0 on the bottom. That is indeterminate. I cannot use direct substitution when I get that indeterminate form. So let's try one of our other strategies. Going down the list, I see factoring comes next. So let's try to factor. And sometimes you can try this in your head, but usually you want to write it down. The limit as x approaches 1, I have to write that because I'm still going to have x's. The top factors into x minus 1 times x plus 6, while the bottom is still x minus 1. I see that x minus 1 cancels out on top and bottom. Therefore, what I have left is x plus 6. So now, with what I have left, I can try direct substitution again. So let's try direct substitution again, meaning let's plug the 1 in here. 1 plus 6 is 7. Now it worked. Done. You may notice that I'm not circling my answers. We want to get used to that because on the AP exam, you don't want to circle your answers. I'll explain more at another time. Let's look at the next one. If I try direct substitution, so using direct substitution. A minus a on top, a to the 4th minus a to the 4th on the bottom, 0 over 0. Does not work. It's indeterminate. So let's think about something else we can do. Maybe you can pause the video and try it yourself. Welcome back. That's it. Factoring is going to work. The limit as x approaches a, x minus a over, this is a difference of squares, x squared minus a squared, x squared plus a squared are the factors. This can factor even more. So let's change this into x minus a over, this difference of squares is x minus a times x plus a, with the remaining x squared plus a squared. X minus a cancels out, and with what we have left, we can plug in with direct substitution, 1 on top, a plus a on the bottom, a squared plus a squared also on the bottom. This makes 1 over 2a times 2a squared, therefore 1 over 4a cubed. Keep in mind, even though these are letters, they're not variables. When you see beginning of the alphabet letters, they mean numbers. Let's try another example using this strategy. G of x equals 3x cubed minus 5. Let's plug in what g of x is into here. So let's rewrite this. The limit as x approaches 0 of 3x cubed minus 5. That's g of x, minus g of 0 means plug 0 into g of x. So that's going to be, and I'll use different color to help you, g of 0 is 3 times 0 cubed minus 5. And then that's going to be all over x cubed. Okay, so what you can see here is I took g of x, I put it in here, there's the g of x. This one's the g of 0. Now let's go ahead and simplify what we have. Limit as x approaches 0 of 3x cubed minus 5. This one over here makes negative 5, so minus a negative 5 or plus 5 over x cubed. These are going to subtract out. With what I'm left, the limit as x approaches 0 of 3x cubed over x cubed. The x cubes factor out, and I'm left with the limit of 3, and therefore it's just 3. Let's see what happens when we need to try rationalizing. So this is an example of when we need to rationalize. Rationalizing, multiplying by the conjugate. So instead of square root of x plus 9 minus 3, it will be plus 3. We can multiply it to the top and multiply it to the bottom. If you do a real quick direct substitution check, 0 plugged in here, that gives us 0 over 0. Direct substitution doesn't work. Let me write it out for you. If I try direct substitution before I rationalize, square root of 0 plus 9 minus 3 over 0, square root of 9 minus 3 over 0, 3 minus 3 over 0, 0 over 0. Nope. So let's continue the rationalizing technique. So I'm multiplying this times this. We need to FOIL. X plus 9, square root of x plus 9 times square root of x plus 9. Let's write the limit expression first. That is just x plus 9. Then the outers and the inners are the same but opposites. They will cancel out. Then negative 3 times positive 3, negative 9. All over, I already had an x there, so x times that expression. Square root of x plus 9 plus 3. Now I want to simplify on the top. The limit as x approaches 0. X plus 9 minus 9 is x over that denominator. The x's factor out from the top and bottom to leave me with this. And plug the 0 in now. Notice the limit goes away when I plug in the 0. No more variable. And I get 1 over 3 plus 3, or 1/6. Now, you see that I wrote equals, and then I wrote equals, then I wrote equals, then I wrote equals, then I wrote equals, because all of these are equal. But sometimes it's better safe than sorry. Just leave out the equals, except for this. You don't want something to be next to each other and it not have some sort of symbol. Let's try number 4. Here is an example of we tried direct substitution. 1 over 0 plus 4 minus 1 over 4 over 0. That makes 0 over 0. Direct substitution fails. So we are going to try getting a common denominator and simplifying it into one fraction. So get a common denominator to simplify. I need to basically multiply by each other's denominators. This needs this one for 4. This needs this one, x plus 4, x plus 4. Let's carry it down here and see what it's supposed to look like. Please write limit as x approaches 0. 4 over 4 times x plus 4 minus x plus 4 over 4 times x plus 4. And the bottom, still x. So it's the limit of all of that. This simplifies into limit as x approaches 0 of negative x, if we add up all those, over 4 times x plus 4 over our denominator x. Now, instead of dividing by this x, we can write this as times the reciprocal of it, which, you're right, is 1 over x, multiply by the reciprocal instead of dividing by that term. If we do that, then you're going to be able to cancel out this x with this x. They factor out, and it looks like this. The limit as x approaches 0 of negative 1 over 4 times x plus 4. Now, we got rid of that bad guy right there. We canceled him out. He factored out. So we don't have to worry about using direct substitution now. I don't have to write limit because I'm plugging in the 0. Negative 1, 4 times 4 is 16. Yay! Fifth example. This is a good one to practice expanding out. Now, delta x is a variable. It's not two variables. Delta x, one variable, delta x. If I plug in 0, it's not going to work. So expanding out is how we can deal with this one. That means multiply this out. That x plus delta x times itself, x plus delta x. So remember what that is when you FOIL, x squared plus x delta x. X is a variable, delta x is a variable. They are two different variables. 1, 2. Okay? Inners is another x delta x. X is a variable, delta x is a variable, two different variables. Delta x times delta x squared. Not x squared, delta x squared. It's its own variable. So here's what it's going to look like when we expand it out. Limit delta x approaches 0 of x squared plus 2x delta x plus delta x squared. That was what we expanded, this part. And then we have this part minus x squared. And then we still have the denominator delta x. Now we can combine some like terms. Rather, they get rid of each other. So this becomes the limit as delta x approaches 0. These two guys subtracted away. With what we have left, we can factor out a delta x. So I'm going to factor out delta x, and what's left over from the first one is 2x and 1 delta x from the last one, all over delta x. And there you see, again, those factor out. I got rid of the bad 0 denominator. Now I can try direct substitution. 2x plus 0, because remember it's delta x goes to 0. Delta x goes to 0. And that's right, our answer is going to have x in it. The answer is 2x. Done. Looking at some of these, we tried Rect substitution first. Tangent of 0 over 0. Well, guess what that makes? 0 over 0. Yikes! Can't do that. So let's try a special trig limit. Remember what they are, guys. First one has sine, second one has cosine. Well, this one says tangent. No biggie. Let's change tangent into sine and cosine. So instead of tangent, I'm going to write sine of x over cosine of x. But remember that that was all divided by x, right? Divided by x. But remember, instead of dividing by x, we can multiply by the reciprocal. Multiply by its reciprocal. So it can look like that instead. Now we know our commutative properties of multiplication tell us that we can write this instead as the limit as x approaches 0 of sine of x over x. See, we just moved this guy under the sine of x times 1 over cosine of x. We just moved that guy over here. Commutative property, no big deal. Then using our limit properties, limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 1 over cosine x. This one we've memorized and we know it. Yay! This one is 1. This one we use direct substitution. 1 over the cosine of 0, and we know the cosine of 0 is 1. So this turns into 1 times 1, which is 1. Yay! Next example, also using a special trig limit. This 5 right here. Can't pull it out. So it looks so close to that special trig limit of limit as x approaches 0 of sine x over x equals 1. But that 5 is there. But we don't have to think of these as x's. We can think of this as the limit as theta approaches 0 of sine of theta over theta. It doesn't matter what that variable is, which doesn't matter if this says 5x, as long as the bottom says 5x. So if I multiply the bottom by 5, I'm going to multiply the top by 5, and then using my limit properties, I can pull this 5 out. So now it looks like this. 5 times the limit as x approaches 0 of sine of 5x over 5x. So now that you see theta, 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 whatever variable that is, same here, and oh, well, almost the same here. But let's think logically. If x is going to go to 0, then where is 5 times x going to go? Yep, also it's going to go to 0. So we can assume that that's true too, because it is. So this turns into 5 times the limit as 5x goes to 0 of sine of 5x over 5x. Same, same, same. This guy is 1. So really we're writing 5 times 1, which is 5. Yay! Next, well, this looks really similar to my special trig limit of cosine 1 minus cosine x over x, which we know equals 0, cosine. 3, that bugs me, but it's not in the cosine function, so pull it out as 1/3. So rewrite this, 1/3, limit as x goes to 0 of 1 minus cosine x over x. 1/3 times 0 is 0. Yay! Pause the video, try a couple more examples, come back. I'm going to work through these. This is the same as saying 1 over the limit as x approaches 0 of sine x over x. Reciprocal property. This is the same as saying 1 over 1, which is 1. You got it. Check it out. Asterisk, AP problem. Very important. You might see it on a quiz. You might see it on a test. Pay attention. If we try direct substitution, it doesn't work. Lots of ways we can try to do this otherwise. Sine squared of theta, we can use our Pythagorean identity, change this to 1 minus cosine squared of theta. Then this is a difference of squares, which can be factored. Factor that difference of squares into 1 minus cosine theta times 1 plus cosine theta. Let me write what you have after you do that. The limit as theta approaches 0. 1 minus cosine theta over 2 times the quantity 1 minus cosine theta times the quantity 1 plus cosine theta. See our 1 minus cosine thetas, factor out, and with what I have left, I can use direct substitution. I get 1 over 2 times 1 plus cosine of 0, which is 1 over 2 times 1 plus 1, which is 1/4. Woo! Another AP problem, got it from an AP test. Pay attention. Secant, if I plug in 0. Direct substitution. Well, remember what secant is. It's just the reciprocal of the cosine function, and I can evaluate that. That's 1 over 1, so 0 times 1 is 0. No fancy tricks there. That was an AP question. What? You can do it.